Hello students, welcome back to my YouTube channel PT Tutorial, and today in this video I am going to prove Green's theorem, which is one of the important theorem for BSc and MSc at the same time. Okay, let's see the statement. If R is a closed region in a xy plane bounded by a simple closed curve C and phi of xy, psi xy are a continuous function having continuous partial derivative in R, then line integral psi dx plus phi dy is equals to surface integral R del phi upon del x minus del psi upon del y dx dy, where C is transversed in the positive direction, that is anti-clockwise direction. The statement is saying that we are going to take any region, closed region R. Okay, so we are going to take this region, closed region R. Suppose this is the region R, closed one, bounded by a simple closed curve C, and this closed region R is closed by a simple closed curve C. So the name of this curve is capital C, and this capital C is in the anti-clockwise direction, which is positive direction. So we mentioned the sign here, anti-clockwise direction. Okay, now in this closed region, phi xy and psi xy are continuous function. Inside or the points on the circumference of this closed curve, for this function phi xy and psi xy are continuous function, and their partial derivative are also continuous in this region R. Then we have to prove that the line integral of this is equals to surface integral of this. So we are going to prove this surface integral and line integral by, we are going to start from here. Firstly, we are going to find del psi by del y. After this, we find del phi upon del x, and we find a difference, and we just prove that this is equals to this line integral. Okay, let's move on to the figure. Firstly, suppose that the region R, capital R, is such that any line parallel to either coordinate axis meets the boundary C in at most 2 points. What is the meaning of that? So we have to take the region R in this way, that if we draw any line parallel to y-axis or x-axis, it cuts the curve at maximum 2 points. If we draw the line here, it does not cut the curve at any point. If we draw the line here, it makes the tangent and it cuts the curve at 1 point. If we draw a line parallel to the x-axis, it will cut the curve at 2 points, maximum at most 2 points. Let the region be included between line x is equals to a, b, y is equals to c, y is equals to d, as shown in the figure, that this region or curve is between these coordinates. Okay, let's move on. So I am keeping this figure here, and I am going to write something. Let the equation of curve APB and BQA denoted by C1 and C2 be y is equals to f1x and y is equals to f2x. So we are assuming this curve APB and BQA, C1 and C2. So this side is C1 and this side is C2, and equation of curve is equals to y is equals to f1x, f1 y is equals to, for this side y is equals to f1x, and for this side y is equals to f2x. Okay, after that, now we have, firstly we are going to find a surface integral of del psi upon del y dx dy. It is already here. Okay, now double integral del psi upon del y dy dx. So we are differentiating or integrating it with respect to y first. So range of y is from where to where? We are taking the y from f1x to f2x. So the lower is f1x, y is equals to f1x, y is equals to f2x, and x is equals to from this a to b. So we are taking the integral a to b. Now we are applying integration over partial derivative. So it cancels it out and it will become psi xy. Psi is the function of x and y. f1x lower limit, upper limit dx. Now we are going to put these limits. We get a to b psi x f2x psi x f1x dx. Now we are going to integrate it with respect to x. What we will get? After changing the order a to b, if we can write b to a, it will become minus integral b to a. I hope you know this property of integration, f to x. This is minus a to b, we keep it simply as before, x f1x. Okay, dx dx. Now minus b to a psi x, f2x is equals to what? We consider it f2x is equals to y and f1x is equals to also y. f2x and f1x both are equals to y. So we are going to write it y here, dx minus a to b psi x y dx. So we are taking the minus common from both integration. So the f2x is the equation of the curve C2 and f1x is the equation of the curve C1. So you may write it C2 here, psi xy dx plus C1 psi xy dx. Okay. If we integrate any surface, any closed surface in two parts, after adding their integration, we whole integrate the surface. So this is the integration of whole surface dx. So this is the integration of whole curved surface C. We consider it as number 1. Similarly, we are going to draw one more closed curve and we take the stripes in this time with parallel to x-axis. Parallel to x-axis. This is y, xy coordinate 0. This is again the same. This is x equals to a, x equals to b. This is y equals to c, y equals to d. This is a, p, b, q. This is anti-clockwise. Okay, nothing get changed. Next, let the equation of curve, now we are taking the curve in this way, PBQ QAP. Okay, equation of curve QAP and PBQ denoted by C1 dash and C2 dash B. So earlier we take the stripes parallel to y-axis and the equation of curve is in term of x-axis. This time we are taking the stripe parallel to x-axis, so the equation of curve will be in terms of y-axis. So x is equals to g1y. So g1y, the curve QAP. This time this side curve is, what is the equation of the curve of this side? g1y and this is g2y. Okay, and x is equals to g2y respectively. Then we repeat the same process again. I hope you understand. double integral r. Now we are going to find this time del phi upon del x dx dy. Del phi upon del x dx dy. Now we are integrating the x here. So x runs from x is equals to g1y to x is equals to g2y, and y is equals to c to y is equals to d. Integrate it, c to d. After differentiating and integrating at the same time, it cancels out the function phi xy, left with the lower integral and upper integral dy. So we are going to integrate c to d phi g2y y dy, c to d phi g1y y dy. Okay. Again we are going to change the order of second integral. C to d phi. In place of g to y we can also write x, because we assumed it here. X is equals to this and x is equals to this. So this will become xy dy. After changing the limits d to c, this minus minus become plus and it will become d to c phi. In place of g1y we will write x y dy. Now again this integration for g to y, consider this function g to y for the curve c2 dash phi xy dy plus integration c1 dash phi xy dy. So we get the integral. Line integral for the whole closed curve C phi xy dy. Take it equation 2. Now we are going to subtract equation 1, that is r del psi upon del x dx dy is equals to line integral psi xy dx, number 1, and we find the second equation del phi upon del y. Sorry, this is del y, this is del x dx dy is equals to line integral phi xy dy, equation 2. Now subtracting equation 1 from 2 we get, okay, subtracting equation 2 from 1 we get surface integral r del phi upon del x minus del psi upon del y dx dy is equals to line integral phi xy dy minus psi xy dx. So I tried my best to explain the Green's theorem in a very simple way, in a very short term, in a very short time and with better explanation. So please subscribe my channel if you like this video, and thanks for watching my videos.